Okay, guys, let's get underway, stay on time. Kind of move beyond the basic model and start to consider a couple of issues that come up. The first thing I want to kind of raise is maybe we don't want to just restrict our parameter space by putting a theta parameter on the systematic U's. That would be one way of kind of restricting the model rather than just exploiting the CCPs to get the U's and going from there. Maybe there are other ways that we would like to restrict the model, and a natural way might be in a non-stationary setup that we don't have all the time periods that are relevant for the agent's horizon. I would argue that that's true of, or at least an important factor that could be addressed in many, almost all studies of industrial organization because of technological progress and how difficult it is to imagine that we are in a stationary world. I think it's more generally the case, as for example, even in life cycle models, we may have what we'll call a synthetic cohort. Some people young, some people old, stitching together a lifetime. But the young people that are alive today probably won't experience the same kind of future that occupies my current status. And so in that sense, I think non-stationarity is a fairly pervasive phenomenon. And that's a problem for us because it's hard to see even what kind of trajectories people are imagining for themselves as they think about future. Now, in line with what I said before, I have no problem imagining that people have rational expectations in the sense that they can think about what would happen to them in the future way better than I can, as an economist, could think about what will happen to them. So yes, rational expectations is a terrible assumption because we economists don't know nearly as much as the actors whom we presume to model. But, you know, it's the best we can do because it's very hard to model people who are more sophisticated than we are because they have a whole lot more detail than we have about the situations that are relevant for them. So yeah, we retreat to rational expectations. But even in that setting, or more generally, in a setting where maybe they don't have rational expectations, but in some sense, common expectations about what might happen to them, it's hard to kind of imagine what kind of path they'll actually enter. And so in this kind of setting, the sampling period, when we look at the agents, often falls short of the length of time that these people will be planning their own features. So we look for another kind of assumption that might help us be able to say something about counterfactuals. The something is kind of limited because we've already acknowledged that we don't know what the future holds. So how are we supposed to predict what the future holds for them when we don't have any real data about what could happen now that we're backed out of a stationary environment? Well, one thing we could do is say something like the following. Here is the period that we look at between here and here. Maybe we could say something about what would have happened if there was a counterfactual regime in between here and here. Still in the past, but saying something about what that counterfactual would have involved. Now, that's a very limited thing. I understand that. We only observe people from 0 to S. From S to T, we don't observe them. And all we're saying is, well, if you'd done this in this phase of your life, under some circumstances, perhaps I can tell you about what might have happened in this other regime. Yes, very limited, but the issue is, do we really have much right to go, or much, put it another way, expertise in going beyond the data and the logic that we bring to our models? I'm starting to sound very much like a causality person. I'm not, but my point of departure is more, yes, I'm willing to talk about different regimes, but only when they're structured within an overall framework that I feel comfortable with making those kinds of assumptions. So here we are. We have a sampling period that falls short of the whole cap T. And we would like to use this representation thing that I talked about in the previous lecture. And instead of telescoping right out to the end of period T, we only go up to period S and stop there. And at period S, we then just plug in the social surplus function that could be reached in this world. Unfortunately, B is endogenous. It depends on what occurs after the sample ends. There are capital X of them. So this is a vector here. Our model's not identified unless we impose something on this thing. Okay, we've got to do something about it in order to be able to estimate this U, because what people do is driven not just by what goes on inside the sample, but also outside the sample. And that's pretty important, for example, if you're talking about people who get their PhDs, right? Because it can't be that the wonderful amount of consumption value that you get by listening to me is the reason why you're doing a PhD. It has to be that it's the future earnings and the future kind of life that you'll have, which is driving you to what's in this lecture hall. Okay. So how do we do it? Can we get anywhere in this situation? Sometimes is the answer. Let's suppose that we could think about a set of weights such that when people followed those weights in terms of their quasi-mixed strategy play, had nothing to do with optimality. Remember, these weights could be negative as well. So that out at some period, row periods ahead, the distribution of those X's, distribution in that loosely put way that they have to sum to 1, not necessarily positive, that regardless of whether you start off with taking action little j or action little I, follow these weights. One is specific for when you start out with action I. One is specific for when you start out with action J. Regardless of which way you travel, following these weights, you will end up at the same, we'll call it distribution, row periods out. Or more generally, maybe you don't start out at action J, maybe you start out at some mixing action to begin with. Okay. And so we work out what the weights are and compare it with some other. Okay. The point is, after so many periods, you end up with what I'll call a probability distribution that is the same regardless of whether you started out taking this action versus that action. Let's think about what's going to happen. When you follow through with these weights, you're doing all kinds of non-optimal actions, right? Because these weights are telling you to take actions which are non-optimal. But we already have those value correction terms in there. And so when you're taking these non-optimal actions, you're doing this, you're adding to your utility, if you like, a correction factor to reflect the fact that you took a non-optimal action. It's almost as if we're compensating you for following these omega weights instead of going through with your optimal action. Now, we're only doing this out to row periods, and row's not very far ahead, right? Be 1, 2, 3, a few, okay? And as a result of that, at least up until the last few periods of the sample, we've got your CCPs, because we know those correction factors depend on the CCPs. The CCPs are things that are gonna determine those correction factors. And so we will be adding those things in to the utilities that you're getting, and in that way, controlling for the fact, if you like, that you're not taking optimal actions. No problem. So if there is finite dependence, we can now think about differencing what would happen if you took action J versus action I. Because what you're really doing here is, if we go back to this one, we're saying, let's take action J, okay? And we think about what's the difference between the utility that I get, look at this utility representation here, and then a similar equation for I, okay? And then over here, we're going to have different kappas, different transitions, because in one case you start out with I, and in one case you start out with J. And so you'll be using different omegas, which are then given to you. Oops, that's wrong. Sorry. Oh, I know. That's on a previous set of slides. Those kappas are formed from where you get to when you follow those omegas. Remember, I said that, well, you might remember, I said just before lunch, I said when you're putting forward those different kinds of actions, those weighted actions, that is going to then determine what those kappas are. Okay. I think I'll leave it rather than trying to recover my previous set of slides. But anyway, the kappas come from putting together the transition functions with the omegas that you've taken. And so these kappas should be perhaps superscripted by the omegas to reflect the parts. So we've got a uj minus a ui, and then we're going to subtract stuff from one from the other. And the point is, out of this stage, when you get out far enough, in fact, row periods far enough, they're going to cancel. And so that's the sense in which we can get a representation for these utility. Here we are. I'm sorry, I'm going the wrong way. Here we're getting these, this is the equation that we end up with, let's put it that way. We've got the difference between the current utilities, okay? We've got the correction factors for the current periods. And then we run this out row periods. See, we're starting out from T and then we're going out to rho, T plus rho. And in that period of time, we might have started out with the I set of, we start out with action I, and then in that case, we got to get, those are the weights, or we started out with action J, these are the weights, and so we're differencing the weights, because if we go action I, there'll be one set of weights, go action J, there'll be another set of weights, difference the weights, those weights reflecting where we'll be at any given period down the line. And not only that, where we'll be in terms of the states. And that is why we have the utilities associated with reaching each of these different x tau states all the way through from period T now until T plus rho later. Maybe I should say this a slightly different way. We're thinking about the difference in utilities that you'll get going down one path versus going down another path. Once you get to T plus rho periods, the distribution of the X states will be the same. As a result of that, you'll be in the same position. From then on out, if you follow these separate paths, at least in terms of the distribution, you won't have cared whether you have gone down this path or that path. Okay? It's not that you actually have to end up at the same point, of course, just that the distribution will be the same, because you're doing it in an ex ante sense, asking where will it be in the future? So the difference between going down one path versus the other path can be caught in those first row periods. You completely capture it, because after then, the ex ante, the social surplus function, expected social surplus function, only conditioning on what we know right at the beginning, will be the same tau plus rho periods later. Okay? So what we have here is the difference between utility J and utility I being something that depends on the CCPs and then funneled through the value correction factor. So this is just going to be, once you've estimated from the sample, this is just going to be a number. This is what typically type 1 extreme minus log P, where P hat, where this is estimated. And then you've got all the different utilities that can occur between now and T plus rho, where, and those things will depend on typically on parameters. So we're estimating parameters here, we're estimating parameters here and here, but we've got numbers here and here, okay? And then over here, we have the weights which you've chosen, because you're going to specify those weights carefully. And these kappas are going to depend on, well, the transitions that you get when you follow those weights. So that will depend on the estimated transition probably from one state to the next when you take a given action. So you have sample analogs in that, for example. And also the weights themselves. So these are numbers that get plugged into the estimation routine. These are numbers that get plugged into the estimation routine. And if the model was correct, and you plugged in the population analogs to the sample instead of the sample, well, then that equation would hold exactly. But of course, you've estimated the P's and the F's that go into the kappas. And so what you have is the model not with the first round estimates, the pre-estimates, if you like, not being exactly correct. And so you will minimize the distance by choosing your parameters of the U to minimize the difference between this and that, say in a quadratic sense, say a minimum distance estimator. That would be way to go. In other words, we get a model from the theory. Here it is. We plug in our estimates for the CCPs, wherever they're supposed to appear. We've got a set of weights that guarantee that that equation that I was talking about on the previous slide with the kappas being equal to each other after a while. And then we just estimate the squared distance of this minus this. Okay. So for example, suppose U is linear in X, which is what the kind of example that you'll usually use. And so here you've got it something linear. It's obviously got a closed form solution. Okay. So that is how we could apply finite dependence in estimation. Again, it's a consistent estimator. It's going to be asymptotically normal, root n consistent, obviously root n consistent in the case where the when you've only got a finite number of states, but more generally it'll be root n consistent even if X is a continuous random variable. Notice that we're not making any assumptions about what happens to the person after the S periods are done. We have a sample that goes to total S. We're not making any assumptions at all about what's happening about the outside that sample period. And think about, well, what would you do if you didn't apply finite dependence? It's going to depend on what you do is going to depend on what the agent thinks about what's going to happen later, right? So you're probably going to have to parameterize what's going to happen to all those states after S ended, even though you've got no data on that at all. So that's the kind of trade-off that you're making here. On the one hand, if you say, I'm not willing to make assumptions about that, I'm only willing to talk about, here's what happened in the data, and here's what would have happened to this population if they'd been exposed to this treatment versus that treatment. I am not willing to talk about something that's outside of my, I'm going to say can. Okay. Now you might have good reason to do that. You might have good reason to go beyond what the data says, and that's fine. I mean, I'm not questioning that. It's just that I have no expertise in that area. And you would want to have expertise in that area to be able to talk about what's going on outside the sample. Otherwise, how presumptuous to start talking about what's outside of the data when you've got less expertise than the people who are actually doing the job. So that's why we go that way, but that's also why we're kind of limited in what we're kind of willing to say. So, as I've said, plug in the transition terms, form the transition probabilities using the weights, estimate the CCPs, plug the CCPs into these terms, go ahead using minimum distance. All right. That's how you approach this. And now I want to talk a little bit about when do you know when you've got finite dependence? Well, let's just go back for a minute before I talk about that to the definition of finite dependence. These kappas are formed from the weights and the S, right? They have nothing to do with the utilities. So the issue then is, are there a set of weights so that sometime not too distant in the future, this thing is satisfied? Well, we've already made assumptions on the transition Fs. We can estimate those guys. The issue then becomes, are there a set of omegas so that this equation is satisfied for all the different states, t plus rho periods ahead? So in principle, this is something that's testable. Has nothing to do with the utilities. And so, of course, if we had a very fast computer, we could go through and ask, okay, do we have one period dependence? Is it true after one period for a set of weights? Is it true after two periods? Blah, blah, blah. Okay. So we can make some progress on that. And one of the articles with Peter Astidiakonou tries to work through an algorithm in which we say, okay, these are the kinds of things you can check. These are the kind of determinants that have to be invertible. Go from there. It's, I would say, incomplete, but it's a start, I hope. But that, in principle, shows you more or less where we are in terms of thinking about, are there algorithms that help us move forward in checking out whether this holds or not? Clearly don't depend on utilities, clearly depend on just transitions, clearly depend on how you choose the weights. There are all kinds of different ways. What kind of determinants have to be invertible in order to be, or non-zero, in order for the right matrices to hold up so that these things line up. That's kind of where we are. That's not what people do. Not yet, anyway. Not in real applications. In IO, the standard application is to say, well, each of the firms has a chance to liquidate. Just move out, all right? And in that case, we've got the transition, we've got a choice that pushes the firm right outside of the game, and that simplifies things quite a lot, okay? But even in, I won't say but even, also in labor economics, we often assume there's a terminal state. For example, some of my work, people are in the executive suite, they're managers, CEOs, whatever, and then they leave. In these kind of situations where you've got a choice to end the dynamic program, choice that says, okay, I'm leaving now and I get a scrap value. In those cases, we have something called a terminal choice. It has an absorbing state. And in that case, we might denote the first choice, say, as the terminal's choice. At that point, whatever happens from that point onwards does not depend on where you were before, because it's over. Had a wonderful life or something. And so if we were thinking about how states evolved from taking one action in one period versus the next action, given that 2 periods out, you retire for sure, or you retire as soon as you can, we'll note that, well, how does this work out? We're asking, what is the distribution of X in 2 periods out? Well, that's just going to be not dependent on, this doesn't depend on what happens in the second period because you're returning, okay? Because you're giving up at this point, so you can pull this out. Then you're summing over the different states that you might reach tomorrow. It's equal to 1, obviously. And so you're just left with this guy, okay? So if we were to set the weight equal to 0 for every state that's not equal to the retirement state, go back to what we'll call equation 2. Let's look at that for a minute. We're asking, how does that work out? We just have the difference between these two utilities, in this case, has the current corrections, here they are, but moving on just one more period with this terminal state in there, we end up with this, just this FJTXT. In other words, and you can check the algebra later, go to this guy. This is what we're talking about. From 2 periods out, it's the same. So it already cancelled. Okay. So you're only concerned about the next period. You've set the omegas up in the way that I said. In other words, retire as soon as you can. In one case, you retire straight away. In the other case, you retire 1 period from now. And then you've got, well, there's a 1 period transition. That depends on just what you're going to do in the meantime. You've got the correction factor in here. And that's why you've got the correction factors and the utilities for next period, as well as what can happen to you when you take action J now. And so that's all there is. So in other words, when there's a terminal state, when there's a chance that you might decide to stop having kids, and that was the original application of this terminal state within this context, in that situation, you only have to go 1 period out into the future. And so you're looking at correction terms today, correction terms tomorrow, and that's it. That is a result of 2 things. Number 1, the model being the general model that we talked about, dynamic optimization model. That's number 1. Number 2, we've specified the distribution of the disturbances, say type 1 extreme value or whatever, and we know what it is. And as a result of that, we know the psi correction terms. Okay. And number 3, that we have this terminal state. In other words, we have finite dependence after 1 period. And so we're making that assumption on the transitions, which we can test. Okay, because I said you've got the transitions, we can see the results of these different actions. Is it really a terminal state or not? Do people, for example, do reverse? Well, do they reverse the terminal state in some way or other? So that's one situation where people have used this assumption quite a lot, and that's the context in which it's used in IO sometimes. Second case is in a renewal model, and the key about a renewal model is not that you're quitting, but you're starting again. And so when you start again, whatever state you were in the previous period is irrelevant. So it is still true that you haven't finished your dynamic optimization problem, but it is as if you've chopped down a tree and planted another one. And so the value function that you might have had before is going to be similar to the value function that you might have now. Or maybe it's not. Maybe there's climate warming or something, and maybe our data isn't good enough. And so maybe you don't want to have that stationarity assumption because because the conditions in which you're planting your trees or whatever have changed. And as a result of that, the value functions changed for the future. But you know it as an agent. We don't know it as econometricians, but it's still a renewal problem. Okay. So in that case, we've got that the state variable next period doesn't depend on the current state because you're starting again. Again, this is an early one. Stuff I did on job matching has that feature to it. And the stuff that John did on replacing a bus engine has that feature as well. And in fact, that is the empirical application that you're going to be looking at next session, excuse me. So in this case, what happens in period t+2 is not going to depend on the state in period t+1. And so the marginal is equal to the conditional. And so that's what's going on here. Well, it doesn't depend on what happened to xt+1, so you can pull it outside. This sums to 1 and you're back to that. Okay? So again, coming back to equation 2, instead of having the sort of mess that we have here, because we're now only have to go out one period, we're just replacing this whole stuff, just one period from now, with this one, okay? And so again, we can just sort of plug this into the likelihood if you wanted to, it's what we'll call pseudo likelihood if you like, because we can almost treat this as a discrete choice problem, static discrete choice problem, go from there. Or alternatively, we could just use that minimum distance estimator that I was referring to just a couple of slides back, okay? In other words, that equation has to hold exactly. We're plugging in estimates of things that we do up front. And so why don't we just estimate the U's after we've done the plugins up front? And then if you want, go from there, make it more efficient, subject to the caveats that I talked about before. Well, can we go further? How do we get finite dependence? So these a couple of little examples to show how finite dependence might arise. One, when maybe it takes more than one step, because a lot of problems don't have one-step finite dependence. We could consider the following model: labor supply and human capital. Just as a very pretend kind of toy example. You can either work or stay at home. You accumulate human capital by working. In particular, if T is greater than 1, you just add to your human capital by 1. But when you start off, there's a chance you get a real boost to your human capital. And so there's a probability of 0.5 that you'll accumulate 2 units rather than just 1 unit. And so with probability 0.5, you accumulate 2 units. With probability 0.5, you only accumulate 1 unit. So for the most part, human capital increases with work by a unit, except in the first period. It might jump to 2, okay? So does this have finite dependence? Well, here's a proposal in terms of weights. This is just guess and verify, okay? As I say, Peter and I have done a little bit of work trying to map out algorithms that allow you to get at this more systematically. But the guess and verify method is what's usually used. And then people can do the quote verification by doing, if they wanted to, a test, or just impose it, which is often what people do, in fact. So here it's a little bit hard to see exactly what's going on, because you have to think about what the 1 and the 2 mean. So let's just go back just for a minute. 2 means work, see that? 1 means stay at home, okay? So let's try and interpret what's going on by remembering that 2 means work, 1 means staying at home. So here, 1 means staying at home. So if you start out by working, stay at home, and you've got the weights have to sum to 1. So that's why one of them's 1 and one of them's 0. And then the other one is is this work versus stay at home. And here is it's really obvious, because if you've already started working, well, one way of achieving finite dependence, an obvious way, is you work one period and not work the next, or not work one period and work the next. In both cases, you add your human capital by 1. And so at that point, you'll be in the same situation. So do you take the course this year versus next year? Well, provided all that counts is this, what your CV looks like after 2 periods, and the order doesn't matter, well then you would have this 1 period finite dependence for that kind of situation. And in fact, that kind of framework has been used in education and human capital accumulation type models. But what about at t equal to 1? That is where it's a little bit finicky, because you might get 2 periods of, you might get 2 units of human capital in that very first period. So you can't achieve it quite as easily after the second period. So in that case, what you could do is stay at home 1 period, and then the next 2 periods work. Okay. How many? Sorry. That's okay. Sorry? Oh, good. Good. I think good. Or what you could do is work in the first period and only work in the second period if you had bad luck and accumulated 1 unit of human capital that very first period you worked. In other words, if you manage to get 2 units of human capital that first period you work, don't work the next period. If you didn't accumulate 2 units of human capital, just 1, well then just work both the periods, and then you'll have 2 units at the end of the second period. Okay, that corresponds to up here, because what you're going to basically, corresponds to what's going on here, because in that case, you don't work this period, but you work the 2 following periods. In both cases, well, regardless of whether you go here or here, you'll end up with 2 units of human capital. Now, we can play around with this human capital example in a different kind of way and show that, well, after all, you don't really have to achieve the same level of human capital, providing that you just have providing you just have the same distribution. That's good enough. And so what you could do perhaps is work here, and you might get 2 and you might get 1. All right. And up here, you work for the first period and the second period with probability of half your work in the following period. And then in that case, you would also have probability of a half of having 2 units of 1 unit of human capital, probability of a half of having 2 units of human capital in both situations. Okay, so that's another way of achieving finite dependence in this case. So there's not a unique way, and that raises the question as to what's the most efficient way. And that's something that really hasn't been addressed, although it looks as though it could be, in principle, at least quite standard. Here's another one that I want to look at. And the reason I want to look at this is because I want to argue that these negative weights can arise quite naturally in these kinds of models. It seems a little bit strange to have probabilities that are negative. They're not probabilities then, of course. But these weights, that's why I call them weights, because it's easier to talk something that downweights something and upweights something, as opposed to probabilities. So we got a simple search model. All jobs are temporary, saying only lasting 1 period. Typical as used to be the case in Spain, I guess. We had a whole lot of temporary work. And nevertheless, so very much a toy example. You could stay at home and set that's the 1 equal to 1. 1 means staying at home. Or you could apply for employment. And applying for employment means that you might get a job or you might not. okay? And in fact, job applicants are successful lambda T of the time, all right? Where that's, say, some likelihood of being employed, depends on the conditions in the aggregate, in the economy, say, and varies over time. Experience increases by 1 unit with each period of work, and say doesn't depreciate. Maybe, so your wage or your utility more generally depends on the amount of experience you have. You just roll up there and say, I've got 10 periods of experience. Maybe that means you get a higher wage, but in this simple case, does not affect your probability of getting a job, although you could easily extend the model to account for something like that. So how would we achieve finite dependence in this search model? Well, one thing you could do is you stay at home first period, and then you apply for employment with a sort of a mixed strategy. That is, you apply for employment at the rate of lambda T on lambda T plus 1. Okay, now I'm not saying that is less or greater than 1. I'm just saying these lambdas are both positive numbers. And so this is going to be a positive number 2. And we won't apply for employment with 1 minus this number. Okay. So the weights add up to 1. So that is one thing we could do, stay at home and then employment at that rate. Another thing we could do is seek work now and then stay at home for sure. Okay. So we're seeking work this period, but next period, we're going to stay at home. Now we attain 1 period finite dependence, because in both cases, I will have increased my human capital if I follow this strategy with probability lambda T by 1. And I'll have the same amount of human capital as I have today with probability 1 minus lambda T. Okay. So it's easy to check, just following these lines, that the distribution of human capital 3 periods out, xt plus 3, is the same, regardless of whether I follow this strategy versus this strategy, and that I'll have higher human capital by 1 unit with probability lambda T, 1 minus lambda T. Okay. Look at what that implies. Suppose lambda T is greater than lambda T plus 1. Well, in that case, this one is greater than 1, and this one is negative. So here we've seen in a very simple example how the weights might be bigger than 1 or smaller than 1. They sum to 1. And it was in a very simple setting where the transitions of how human capital changes just vary from period to period. And so that's the sense in which I would want to argue that you shouldn't discount the notion that the weights might be negative, because that essentially leads to a set of equations that you can use in estimation. Nothing special about it. You can extend this to dynamic games, this concept, although it is tough. Because in this setting, you're always got to worry about how people will react to the changes that you make, unless there is a terminal choice. Because if there's a terminal choice, you step out of the game, they will react to you stepping out of the game, but it doesn't affect your utility, you're gone, okay? So that's the special case in which we can apply finite dependence in these dynamic games, but it is not quite restricted, at least all the empirical applications that I've seen that apply finite dependence use this terminal state property. Can you go any further than that? And the answer is yes, but it's difficult. And the reason is, as I say, Rival's response typically depends on the choices that everyone makes in the previous period. And the state variables for the choices that you make include the values of the state variable for their situation as well. So you're thinking of acquiring capital and being super competitive in one period versus not. Well, if you go that way and become super competitive, your rivals are going to notice eventually. And so that's going to get impounded in the state variables. And so now they're going to react to that. Whereas if you don't, well, they'll react to that too. They'll react to the fact that you didn't become super competitive. And as a result of that, you're in a very different situation. We know that for finite dependence to hold, it has to be the case that the industry level of state variables, not just your state variable, but everyone's state variable, has to be lined up. So unless you can somehow guide them into a set of state variables that are common across all the firms, not just yours, you haven't achieved finite dependence. Again, in distribution, but it's work. All right? So think of what you're really doing here. You're imagining that you're in charge of a class and you're trying to make them think a certain way. How do you indoctrinate them? Well, you might try this kind of strategy over here, nice and easy, or this kind of threatening tough guy over there. At what point in the future are those graduate students gonna kind of see you the same way, if ever? Okay? So you've sort of, if you're thinking about, well, where's that going to end up? You're asking, will there be a situation where it didn't matter how you treated them in the end? You're thinking graduate students is a big deal. No, it's not. Think kids. Oh, there it really counts. All right? Because in that situation, maybe what you do over here causes irreparable harm. Versus over here doesn't. You'll never get those sets of state variables to line up because they will react in certain ways. And it makes it hard to sort of undo what hopefully could have been temporary effects, at least if you'd acted in some way. It doesn't have to be optimal. Okay, we're not asking that because we're only econometricians trying to estimate what happens. We're not actually trying to guide people's lives at this point. All right. So the set of problems that Peter and I have looked at really involve each of these players being able to influence their own state variable. You know, that's why I've got the one here. This is the set of state variables Mr. 1 can do. Here are the set of state variables that Mr. N can do, or Ms. N, with these different choices associated with it. And so hence this is just a product of what could go on, where we've got these transitions determining what goes from one thing, one period to the next. Sort of breaking things down that way to make things a little simpler. You've got one thing going for yourself in this setup that's kind of important in thinking about finite dependence in this kind of context. And that is, you notice that people don't react to your current action. They only react to it later on, after they see the effects of your current action on your part of next period state variable. And that gives you a little bit of leverage as an econometrician, you try and construct finite dependence in this way. Because you're thinking to yourself, maybe in a situation, let's take a renewal situation for me, because again, it's going to be period by period, state by state, person by person. You might have finite dependence for some periods, some states, some people, and not all the others. All right, I should have said that at the beginning, even when I was talking about the individual case, but it's true. And then the question is, how many equations do you get with your finite dependence? How many can you use in order to be able to identify what's going on? And I sort of glossed over that. Sorry about that. In any event, suppose you've got a situation where you are thinking about econometrician, looking at one of the agents and asking, how do we get finite dependence here? Maybe there's a renewal action. So maybe the actor in question, the player in question, can always renew. In that case, what you're thinking about doing is you guide them down one set of, you guide the other players down one distribution after taking an action here versus another action over here, and then guiding the players in another way. When I say guiding the players, what I really mean is that these players are just doing their equilibrium best replies given the state variables and the unobservables that they see, okay, and integrating over the others. So they're thinking, the way they think about the problem is, we're always in equilibrium. What would I do? Okay, pulling it back to saying, well, think about those other players as nature, if you like, with their conditional choice probabilities in there for the state variables. They're not thinking about you as a deviant player following these omega weights. That's not how you calculate what they will do. You're thinking, what will they do in this equilibrium situation? Okay? Because, as I said before, what you care about in these kind of settings is your best reply to whatever is out there, whether it be nature, other people, etc. So you've got these, you're thinking about setting this up so that for all the other players, you will reach the same distribution row minutes from now. Good, thanks. Row periods from now, when they go one way, I, when you go one way versus the other way, J. And then with the very last period, you do the renewal action on both sides so that when you're putting together the distribution of the whole lot, the distribution just consists of their set of state variables, which you guided in to be the same, and then you're renewing at the very last point. So at the beginning of the next period, everything's the same. So that's how you can work through a situation like that. It's actually, Peter and I have worked through a numerical example where you've got about 4 kind of quality ladder thing, where you can show that there are about 4 period finite dependence. We just basically numerically calculated it. And again, what we found was these weights are all over the place, minus in the tens and things that are way over 1, okay? Not testing the decimal precision of the computer by any means, but nevertheless, thinking if you were to combine these things to between 0 and 1, you wouldn't get it. So I think that's where I'll leave this one. So I want to switch gears now in the remaining 30 minutes and start discussing another aspect of estimating dynamic programming problems. Gave you a basic introduction, talked about identification, bunch of different, for polite company, first round estimates. And then we said, all right, aside from imposing parametric assumptions, which are then going to open up a bunch of estimation methods as opposed to simply writing down the formula for what the U's are. Then I said, okay, maybe you don't have enough CCPs. You're missing some of the CCPs. Actually, you could miss some of the CCPs in the Markov setup too, or the stationary setup. You might have not have occurred yet, or you might have terrible estimates. So maybe finite dependence is useful there. And in fact, in many of the applications, people do have both stationarity and exploit finite dependence. I would say partly for that reason. So that's a sense in which the data might be deficient. You don't have enough of a horizon out there, or you want to impose parametric assumptions. There's another way in which the data might be deficient, and that is that it might not measure some of the stuff that you really care about. Now, let's be clear, you have a very simple model to start out with. If you generalize by putting a little bit of unobserved heterogeneity in there, well, you're just going to weaken or unsharpen or make your predictions more vague. You're basically saying, my data is not good enough. And that's why I am going to introduce unobserved heterogeneity. Because if I had better data, I would put that heterogeneity in there as part of the data. So let's be clear what we mean by unobserved heterogeneity. It doesn't make the model more general. What it really means is that it's making your predictions less precise, because now you have to integrate over that stuff that you didn't see. And that's the way it should be. If you have less information, you should be a little less confident about what your predictions are saying, not more confident, okay? But from that perspective, it also suggests that we should be careful about when we want to put in unobserved heterogeneity. We need some unobserved heterogeneity of the form of type 1 extreme value or something along those lines, because if we don't, and everything's observed, well, we should be able to predict what people do exactly. We have exactly the same things that they have. We have exactly the same stuff. And so if they make a bunch of choices, well, then it must, with the same set of state variables, and we observe all the state variables, it must mean that they're indifferent between all those choices, right? Must. But if they're indifferent between those choices, what predictive power does our model have? Basically say they can do anything. It's vacuous. It doesn't have empirical content. And so that's the sense in which we rely on the fact that we don't observe everything. Because if we observed everything within our model, we wouldn't have a way of explaining why people go one way versus the other way. And not only that, since people do go more likely to go this way here and that way there, we wouldn't be able to exploit that in estimation if we had a model that didn't have any unobserved heterogeneity at all. So there's a little bit of a conflict, tension there between how we treat unobserved heterogeneity. We need something to make for our models to have empirical content, but on the other hand, the more we include unobserved heterogeneity, the more vague, in some sense, the less confident we can be about our predictions, because obviously we're integrating over stuff that we don't see. There's another reason why in dynamic discrete choice problems, unobserved heterogeneity is a pain. Basically means that we lose identification. At least we lose it unless we impose restrictions on the way the observables enter. Again, fine, as I said before lunch, those are the kinds of restrictions we'd like to impose, because maybe they're testable. We can see whether they hold or not. But if we didn't impose any restrictions and we just said, well, okay, for each set of X's and T's, there is a different U, We don't have restrictions, and then we've got as many CCPs as U's, and then we're done. And so if we wanted to include unobserved heterogeneity as well, we'd lose it. We'd be back to set identification or something. So let's imagine we have enough restrictions in the model so that we can entertain unobserved heterogeneity in a richer form than just IID assumption. Okay, so here we have it, and I'm just going to give you a couple of examples on this one. We've got Mr. Zerker thinking about keeping the engine or replacing it straight away. And in this setting, we'll just change Mr. Zerker's problem a little bit. He has either GM buses or Ford buses. That's counter history, but so what? So we don't see whether they're Ford or GM buses though. So we don't observe S, okay? The type of bus he's got. I want to imagine for a minute that we knew what the CCPs were. We obviously don't know them for two reasons. One is that we only observe sample analogs versus their population counterparts. But even more importantly in this case, that the CCP depends on the unobserved S. We don't see that. So we don't have a way of estimating the conditional choice probability exactly. So if in fact we did know this function, this mapping, so imagine we knew the mapping from X and S to P, we could plug it in and here's our likelihood function and go for it, okay? Now, okay, we could do that. Here's our likelihood. Notice the way the likelihood's written up. No V in there. I've used the CCP type representation where we've got these logs of P's reflecting those correction factors that come about because people don't just care about their current utility, but their future utility. If you go back to the previous lecture, and I'm not going to now, of course, you'll see that this quasi-maximum likelihood estimator has these correction factors to deal with the fact that you not only have the current utility, but I think as pointed out before, in this case, we have this exponential of the log to reflect those future valuation functions, which in this current setup, because there is a renewal problem, takes this very simple form. Remember, it has a very simple form in this case. So the problem with this is that we have a log and then a sum of some summed products, which is a pain. So instead of doing it that way, why don't we go about the following? Start out. At the nth iteration of this data, because it's going to be an iterative process, we'll define this Q object as being, what's the probability that the observation in question is a Ford, given all the history, see all the history of this bus and all the choices that were made. And also conditional on this last estimate, best estimate of our structural parameter, that's the theta. If I can just go back, this theta is coming from current utilities. Along with, of course, our best estimate of the probability, unconditional probability of this being a Ford or a GM, and this CCP function, which I'm just calling P for now, but it's really the function of both the X yeah. So what is this? How is this thing defined? Well, the easiest way of thinking about this is to multiply this here with the bottom line down here, all right? Because this is the joint distribution of S and, well, what is in here? We're looking at this likelihood, and they were asking, what is the probability of these D's emerging given these X's, okay? And so that is the same as this one, okay? Here is the probability of being a type S bar. I just got to make sure I'm right about that. Just go back here a minute. Let me pull that back. Where are we? Yeah. Remember that this is the this here is the probability of being unobserved state S, and in the example, it's the probability of being, say, a Ford, or the probability of being a GM. All right. So here's the probability that you're a Ford or a GM, and then given that probability, what is the probability of observing all of these mileages? Okay. Joint distribution of type of bus and all of these, well, choices, I should say. All right. And over here, it's the same thing. Given the set of state variables that you see, what is the probability of the type S conditional on the choices, given the conditional on the choices that we see over there? And so that's why this guy times this one is equal to that. Okay. So at the nth iteration, we define this probability that it's a type S bus, say GM bus, given everything we know about it, and given all of our estimates of the probabilities and thetas, define that. Then for the next iteration of what do we think about the probability of any given bus being a certain type, just drawn randomly at front end, unconditional probability, just average over all these conditional probabilities, okay? And then we say, well, conditional on this being a particular type of bus, that is conditional on all the mileages that we see and the likelihood, the log likelihood, we just maximize that thing, all right? So one way of kind of getting some intuition about why this might be true is to imagine for a minute that we know this is either a 1 or a 0, all right? In that case, we would get right back to our original likelihood for this framework. We can go just a little bit, oops, we can go just a little bit further than that. So let's move on. Where do we get our CCPs from in this case? Well, really two ways. One is we could just add up the number of expected buses that we think of are a particular type. If we knew what type they were exactly, this would just be the sum of buses that had a particular X value, all right? We don't know exactly the number of buses, but we've got an expected number of buses here. And then we ask, of that expected number of buses, how many of them made say, a replacement engine decision versus a keep on going and do some maintenance decision. So this is almost like the relative frequency approach that we would use if we knew everything about the buses and there was no unobserved heterogeneity. We don't know everything about the buses. In particular, we don't know whether they're a Ford or a GM, so they do different things. And so as a result of that, we say, well, what's the average amount of replacement that goes on given the expected number that I actually see? Okay. And so we could follow through with that one. Or in the stationary environment, we could just say, oh, why don't we just take the likelihood? Likelihood calculated according to this quasi-likelihood framework that I described. Whoops, keep going the wrong way. Sorry, I think I'd learned this by now. The likelihood described, one more slide back, here. Sorry. Here, okay, where we've got these correction factors in the appropriate spots and all the rest of it. So those are two ways that we could calculate this thing. What do we get when we do that kind of stuff? Well, we tried. We had a look at, we made the model just a little bit richer by letting these x's follow a stochastic process about how many miles would be accumulated. These buses had random number of miles. They also belonged on different routes, and so that affected things a little bit differently. We also looked at a case where there was an aggregate shock to the cost of bus engines that Mr. Zerker knew about. He knew, for example, that the cost would go down by this much this period, this much next period, etc. Notice the assumption that he knows. So he has perfect foresight over this. If he didn't have perfect foresight, well, then the problem would be a lot harder, because we then have to think about the distribution of what would happen. Okay. So we allowed this aggregate shock to take place, and that's this basic cost. And then in this setup, because we have renewal property, we basically get an equation that looks like this. You've got the log probabilities for expected over the extra miles that these guys might take, depending on whether you replace the bus now or don't replace it later. Those things come from the data. And then we went ahead and estimated it. We're estimating, notice the beta as well as these two parameters. And this was done quite a while ago, so things are a lot faster now. But when we estimated back then, you can see that here's what happens when it's observed. If you ignore it, if you ignore what type of bus it is, then you really do get biased estimates. And in particular, the coefficient estimates of the various effects are mashed together because they're averaging over buses. And that's not an unusual thing to happen in this kind of setting. And so if you really do have a reason for introducing unobserved heterogeneity, for example, buses of Ford is very different from GM, then yes, I would be definitely advocating including it, because you then have a reason outside the data for differentiating this stuff and hence enriching the model. And in that case, you really do get more precise estimates. As you can see, things are blurred here. Now, if you treat the things as unobserved, well then these are the estimates you get. And you can see for the most part, they're pretty much on. They're done. It's a standard deviations of the Monte Carlos showing that the CCP estimates are not as precise as the full information maximum likelihood. But really the main big difference, at least from this table, is that maximum likelihood takes way longer than CCP, and that's obvious because with a CCP, you're not doing any nested fixed point algorithm in the middle. All you're doing is taking some relative frequency, plugging in them, and then banging out what happens at the end. So that's what happened in this case. And then in the case where there are time effects, well, of course, with the maximum likelihood estimator, you would have to put a distribution over that aggregate shock in order to be able to actually write down what the likelihood function was. But in this setup, of course, you don't, because there's finite dependence and you only care about the thetas that are actually in the sample. And so they just come out as constant. They're very precisely estimated. That's why we haven't bothered including, Peter and I haven't bothered including them in the set of results. And you can see that whether there are time effects or not doesn't really affect the estimates of the structural parameters very much. So I want to go on for one more Monte Carlo, and in this case, settle on a game. Here, we've got entrants paying a startup cost to enter the market, and incumbents don't. So it's cheaper for incumbents to stay in the market than it is for entrants to come in. So we'll say that declining to compete in any given period is essentially saying I'm exiting. Okay. When a firm exits, another firm has the opportunity to come into that slot. So imagine a little strip mall. You've got a bunch of shops on that strip mall. Sometimes people come in, they leave, and the issue is, well, how many blocks are vacant, and how often do people fill them up when the entrants leave? Basically, I think there are two sources of dynamics. One is the entrant is thinking, they're related, of course, is depreciating the startup cost over its lifetime, thinking if I come in, how much I have to pay the startup cost, but in the meantime, I get some rent. So what's the value of coming in? I'll be able to spread the startup costs over its life. And then also, if you become an incumbent, well, that reduces the probability that other firms will come in. Okay, you're basically saying if I come in, well, other people won't come in. So there's an additional benefit for me because I'll get higher rents once I can chase a few of these other guys out. That's sort of what's going on here, because once you come in, their epsilons don't have to be so good for them to exit once you're in, because you are one extra person in there. So those are essentially the two sources of dynamics in that setup. This first one would be in there if there were even in a situation where there's no game. This second one is there because there is a game between these different firms. So permanent characteristic, which we'll denote by x1. And in addition to that, we're going to imagine that there is, and that's just going to be drawn from 1 to 10 values. So talk about the observed state variables. I should have looked at the heading first. There's a permanent characteristic, which stays with them. And there's also the number of people that were in the market last period, number of firms that were in the industry last period, because that's reflecting somewhat the number of firms that are likely to be in the next period, because as I said, once you're in as an incumbent, you're more likely to stay than not. You wouldn't have come in unless that was the case. So intuitively, more people paying entry costs lower the expected number of competitors that are going to come in. But there's something unobserved in this framework as well. And that is this demand is bopping up and down. It's bopping up and down in a very special way, though. We've got a square matrix. It could be in one of 5 states. And if we're looking at the diagonal, it's just pi, okay? And then all of the other states around it, all of the other off-diagonal elements are 1 minus pi on 4. So that obviously the probability of being in any one of the states is summed up equal to 1. But there's really only one parameter, right? The probability that you're going to be in the same state or equi-probability that you'll be in one of the other 5 states. Okay? So that's how this works. And not a very convincing story, I think, because probably the ones that are near the main diagonal elements are more likely than the ones that are far away from the non-diagonal, in the, what is it? Well, the 2 other corners, not the main diagonal, but the off diagonal, those guys would have a lower. But this is what we did for a Monte Carlo. And one other thing to notice here is that we're treating this as exogenous. Because if you don't treat it as exogenous, well, then you've got to worry about integrating the choices that people make in a sequence of periods when there's something sort of permanent that changes over time and changing over time. And you can do that, but if it's endogenous, those choices affect where they'll be. Now, that's been done. In fact, stuff on job matching, I did that. But that was before the days of conditional choice probability. And so since the conditional independence assumption was introduced by John, almost all applications only have exogenous probability precisely because of these, I think, because of these multifold integration problems that continue to dog the profession. It's not as if we should be surprised by that. If in fact data was so easy to analyze, well, then we wouldn't even need computers, or computers would be infinitely fast and we could do integration like that. Well, we can't. And that's why these data reduction methods are two. Okay, that was a fast one.
Bob, I just want to say though, there is this article by Gregor Reich that has solved this. It's called recursive likelihood integration, and that's a likelihood way of allowing serial correlation in the error terms. And of course, there's a work by Andre Noritz with a Bayesian approach that allows serially correlated epsilon terms.
For an infinite number of integrals on an arbitrarily complicated problem, right, John?
Well, it does take more work, but I have a student who's applying this now, and she's able to integrate out over an unobserved state variable. So these are they're like iterated one-dimensional or small-dimensional integrals that can be done.
Okay, thanks. So yeah, all right. So the claim is that these integration problems are apparently not so important anymore. I don't agree. So I think that while there are contributions in this area, I think this multifold integration is still an issue because of the number of computations that are required in order to be able to get accurate, and there's a lot of work has been done on this. And so we'll leave it at that. So in this second Monte Carlo, 2 slides, we get this, write down the utility associated, current utility, with a normalized exit We simulate 3,000 markets. And what do we get? Well, for this low level, again, if we ignore S, we get a serious bias. But when we go through with this method, we can more or less pick up what's going on. The computation time is quite reasonable, 15 minutes. It depends on exactly how we set it up, whether we use the likelihood from the CCP model or the data, or whether we go through what we call a two-stage process here, or if we don't look at the price equation. They're comparable in different ways, but I think since I've run out of time, we should call it a day.